Hey everybody, I hope this video finds you well. In today's video, we're going to be finishing up section 4.5 from your textbook, which was your introduction to the concept of linear independence and dependence. What we're going to be doing in this video is we're going to start with a couple basic properties and propositions that follow from linear independence and dependence. Then we're going to look at a couple more examples of determining whether or not sets of vectors are linearly independent or dependent. And while we do those examples, we'll get to sort of see some of these propositions here that we'll talk about in a moment in action. And then we'll sort of wrap up this section by talking about how linear independence and dependence can be applied not just to vectors, but also to continuous and differentiable functions. And that's going to be an important discussion, not right now in the short term, but for later on when we return to differential equations. But before we do that, we want to talk about these three brief propositions that follow sort of naturally from the definition of linear independence and dependence that we did in the previous video. Now, in your textbook, each of these propositions is also given a short proof. I think each of these statements are pretty self-evident, so I'll leave you guys to read those proofs on your own. We'll just sort of discuss what each of these propositions says. So, proposition number one basically tells us how linear independence and dependence applies to a set that consists of only a single vector. So, this proposition says that a set consisting of a single vector v is linearly dependent if and only if that vector v happens to be the zero vector. So, what that basically is telling us, right, is that you could also phrase this, if we put a note here, note. Another way of sort of phrasing this, a set consisting of a single non-zero vector is linearly independent. So what this is basically saying is that we don't normally run into sets that only consist of a single vector, but this tells us how the concept of linear independence and dependence applies. If that set consists of a single non-zero vector, it's linearly independent. If it consists of a single zero vector, then it is linearly dependent. Another follow-up that you can take away from this is that any set, regardless of size, that contains the zero vector is automatically linearly dependent. So if you have a set of vectors and it has the zero vector in it, that set is automatically linearly dependent. Okay, so that tells us basically how the concepts of linear independence and dependence apply when you only have a single vector. The second property here basically tells us how linear independence and dependence can be thought of when we only have two vectors. So this says a set consisting of two vectors, v1 and v2, is linearly dependent if and only if one of the vectors is a scalar multiple of the other. So this is basically saying in the unique case when you only have two vectors, then linear dependence is the same as one being the scalar multiple of the other. Remember that in general, one of the main sort of things that we showed in the previous video is that linear dependence is the same as at least one of the vectors being a linear combination of the others. Now remember, a linear combination means a scalar multiple of one vector plus a scalar multiple of another plus a scalar multiple of another, so on and so forth. But when you only have two vectors, being a linear combination reduces to being a scalar multiple. And that's all this property is saying. So this gives you guys a very fast way of checking whether or not two vectors is linearly dependent. If you only have two vectors, then you can check for linear dependence just by simply examining if one happens to be the scalar multiple of the other. If that's not the case, well, then they're linearly independent. This proposition, of course, only works if you have two vectors. If you have three or more vectors, then none of them might be scalar multiples of each other, but it is possible that they're still linearly dependent since they might be like a scalar multiple of one plus a scalar multiple of another. So just make sure you only apply this property to when you have a set of two vectors. All right. The third proposition here is perhaps the most important, and it's the one we're going to actually use a lot in the future. What this says is that it says that every set of linearly dependent vectors contains a subset of linearly independent vectors with the same span. And this property right here is a very natural consequence of what we proved in the previous video. If you remember in the previous video, we proved two major things. One, we said that any set of linearly dependent vectors contains at least one vector that is a linear combination of the others. We also proved that if you remove a vector that is a linear combination of other vectors, it does not change the span. This proposition just puts those two things together. It says that if you have a set of linearly dependent vectors, some of those must be linear combinations of the others. You can remove those without changing the span, and once you remove those, your set will be linearly independent, but you won't have changed the span. This also connects to the last idea we sort of mentioned in the previous video, which is that we're eventually headed in the next section to talking about the minimal spanning set. And that minimal spanning set is going to be a set of linearly independent vectors that spans whatever vector space or subspace we're talking about. So this is going to be a proposition that we use quite frequently. Okay, let's get into taking a look at a couple examples, and some of these examples will actually involve these three propositions. All right, so our first example here is we're going to determine if this set of vectors are linearly independent or dependent. So if they are dependent, what we're going to also try to do is find a linearly independent subset with the same span. So our two vectors are both in P2 of R, so they're in the set of polynomials of degree 2 or less. The two vectors here are 2x squared plus 4x plus 1 and 6x squared plus 12x plus 1. And we want to know if those are linearly independent or dependent. Well, we can do this one of two ways. We can do it the way we were doing in the previous video, where we can actually set up the equation c1 times the first vector plus c2 times the second vector equals the 0 vector, and see whether or not that has an infinite amount of solutions or a unique solution. Remember, an infinite amount of solutions corresponds to being linearly dependent. A unique solution, which would be the solution of all zeros as the constants, relates to linearly independent. Or we could use one of the propositions we just talked about, namely proposition 2, that says if you only have two vectors, they're only linearly dependent if they're scalar multiples of one another. It should be pretty clear that this guy here is not a scalar multiple of this guy, because if you multiply this guy by 3, you would get 6x squared plus 12x plus 3, so you wouldn't get this guy here. So we can do this very quickly. So these vectors are not scalar multiples of each other. And since there are only two vectors, this implies that they're linearly independent. Now, as a note, if you guys want on your own, if you set up the equation c1 times 2x squared plus 4x plus 1 plus c2 times 6x squared plus 12x plus 1 equals the 0 vector in P2 of R, which is 0x squared plus 0x plus 0. If you set up this equation, then it will have unique solution c1 equals c2 equals 0. So if you want on your own, you can check this example with the old method of actually setting up this homogeneous equation and find out that it has a unique solution here. Okay, so we're pretty much done with everything we wanted to mention here, right? And we looked at these two vectors, figured out they're linearly independent, and that's, well, we don't need to delete anything, and if we do delete anything, we will affect the span. Now, as just another sort of side note, it wasn't asked for in the question, but let's just go ahead and talk about it anyway. Since these guys are linearly independent, let's just talk about what their span actually looks like. So we'll just do a little second note here. So let's think about what we can say about the span of these two vectors, 2x squared plus 4x plus 1, 6x squared plus 12x plus 1. All right, well, that would be the set of all vectors. That would be c1 times the first guy plus c2 times the second. And if you think about what that actually would look like, if you wrote it as a standard quadratic, it would look like all the quadratics that are of the form 2c1 plus 6c2 x squared plus 4c1 plus 12c2 x plus c1 plus c2. Right? So that's a totally fine way of describing the span of these things, but we could do a little bit better, right? We talked about this concept that sort of where we're headed later about reparameterizing and maybe getting a better view of this. The sort of relation we should see here is that this constant here, 4c1 plus 12c2, no matter what c1 and c2 is automatically double this guy right here, because this is 2c1 plus 6c2. So let's reparameterize. Let's call this guy t, so we have tx squared. This guy then is automatically 2tx, And this, of course, well, C1 plus C2 is not related to these. It's not just some multiple of that. So it would be some other parameter. Let's call it S. Now, again, you guys might be a little shaky about how we know exactly that we can reparameterize this like this, but I just want you guys to sort of think about this. Definitely you should be convinced that this is always going to be half of this, or this is going to always be twice that. So this part of the parameterization should make sense. The other thing that is not a coincidence here is that notice that what we've basically done in this example is we started with two vectors, figured out they're linearly independent, and then realize that the span, the subspace that they span, can be parameterized with two parameters. It is not a coincidence that we had two linearly independent vectors that created a subspace that can be parameterized with two parameters. There's a direct relationship going on here, and that's what we're going to be investigating in section 4.6. All right, let's go ahead and take a look at another example here. All right, so we've got this set of vectors. Oh, we didn't actually say where they're stated, but these guys are all in M2 of R. So once again, we've got these set of vectors, and we want to know, are they going to be linearly independent or dependent in M2 of R? And then we're going to determine if they are linearly dependent, what's a linearly independent subset inside of them. So we've got our set of vectors there, right? Let's go ahead and think about how we're going to do this. Unfortunately, since this is a set of 5 vectors, we're not able to say, is there a scalar multiple, right? If we actually look through these, it doesn't look like any of them are scalar multiples of the others. You might say, well, doesn't that mean that they're linearly independent? Unfortunately not. Remember that proposition 2 only applies if you have two vectors. In this case, maybe one of these is the sum of the other ones, or maybe one of them is 2 times one of them plus 3 times another one, or something crazy like that. We can't just say that they're automatically linearly independent because there's no scalar multiples. So we got to do this sort of the old way. So we need to set up the equation. Well, we'll do C1 times the first one, negative 1, 0, 0, 2, plus C2 times the second one, 2, 2, 2, plus C3 times 1, 2, 2, 4, plus C4, 1, 0, 0, 1, plus C5, 2, 1, 1, 2, and that has to be equal to the 0 vector in M2, which is 0, 0, 0, 0. Okay? Now we can go element by element. So we'll do the 1, 1, then the 1, 2, then the 2, 1, then the 2, 2, and we'll set up 4 equations here. So this would break down as minus C1 plus 2C2 plus C3 plus C4 plus 2C5 equals 0. That would be the 1, 1 element equation there. Okay, then we would get 0 C1 plus 2 C2 plus 2 C3 plus 0 C4 plus C5 has to be 0. Then we would get 0 C1 plus 2 C2 plus 2 C3 plus 0 C4 plus C5 has to be 0. And then we get 2 C1 plus 2 C2 plus 4 C3 plus C4 plus 2 C5 has to be 0. Okay, now we are going to go ahead and put this into like augmented matrix form and talk about that. But I want you guys to realize that if the question was only determine if the following set of vectors are linearly independent or dependent, you could do it right from here. If you think about this, this is of course homogeneous, so it has solutions. We're interested in whether or not the solutions are unique or infinite. Well, we've got 1, 2, 3, 4, 5 variables. But notice, even though I don't know the rank of this, I do know the maximum rank. The maximum rank, there's only 4 rows, so the maximum rank is 4. But if you have 5 variables and your maximum rank is 4, you're guaranteed to have at least one free parameter. So we automatically know it's linearly dependent. In other words, just make a comment here. This system has maximum rank equal to 4. Not saying it does have rank 4, but it has maximum rank 4 with 5 variables. So it has at least 5 minus 4 equals 1 free parameter, which implies it's linearly dependent. Now, this should also make, not only is this sort of clever in terms of the solution sets, but this should make intuitive sense, right? M2 of R consists of 2 by 2 matrices, which basically have 4 different little positions, 4 elements in them. And you've got 5 vectors. That just seems like that's too many vectors to fit all separately from one another inside M2 of R. So it's not a surprise that this automatically is linearly dependent. And I want you guys to see that you can realize that just from your knowledge of solution sets and the fact that this guy's maximum rank is 4. Okay, why isn't this sufficient though to answer our question? Well, we want to go a little bit further because if they're dependent, we want to find a linearly independent subset. So we do still need to go ahead and put this in augmented form and take a look at what the dependencies actually are. But I want you guys to realize the actual fact that they are dependent comes immediately just from the nature of this system. All right, let's go ahead and put this thing in augmented form and then begin to discuss where the dependencies actually are. So we've got -1, 2, 1, 1, 2, 0, 2, 2, 0, 1, 0, 2, 2, 0, 1, 2, 2, 4, 1, 2, and then we have all zeros, of course, in the augmented part. All right, I'm going to do 2 things right away. I'm going to use this guy, of course, to clear that out, and I'm also going to recognize that this guy can clear this guy out entirely. So let's go ahead and do that. Let's replace R3 with R3 minus R2, and let's replace R4 with R4 plus 2R1. All right, so we get -1, 2, 1, 1, 2, and 0. Then we get 0, 2, 2, 0, 1, and 0. Then we get an entire row of zeros here. And then down here, it looks like we get 0, 6, 6, 3, 6, 0. Okay. Now, it's probably a good idea to put this guy at the bottom. So we'll do that real quick. So let's just interchange R3 and R4. And there we go. -1, 2, 1, 1, 2, 0, 0, 2, 2, 0, 1, 0, 0, 6, 6, 3, 6, 0, and then 0, 0, 0, 0, 0 there. All right, now we can use this guy to clear that out right there. So we can do R3 and replace it with R3 minus 3R2. So -1, 2, 1, 1, 2, 0. 0, 2, 2, 0, 1, 0. Looks like we should then get 0, 0, 0, 3, and 3, 0. Yep, that looks good. And then we get 0, 0, 0, 0, 0, 0. Okay, now, again, this guy is not technically in true row echelon form, right? Because we have a leading -1, a leading 2, and a leading 3. You could obviously take it this one step further if you really wanted to. You could do negative R1, 1/2, R2, and 1/3 R3. But this should be sufficient to see that the rank of this guy is going to be 1, 2, 3, which means we're going to have 2 free parameters, which again confirms that it's linearly dependent. Also notice that it shows us that even though this guy had 4 rows, he doesn't actually even have his maximum rank of 4. He actually only has a rank of 3, but even if he did have his maximum rank of 4, it wouldn't have mattered, still would have been linearly dependent. Okay, but we can go a little bit further here and use this, specifically the positions of the pivot positions here, to recognize which vectors are necessary for being linearly independent. So what this basically tells us is that any one of these guys in a pivot position, these vectors are the ones we want to keep that are linearly independent. Why is that? Well, you can sort of think about it that as you're solving this, you let the other ones, in this case, you would parameterize the 5th and the 3rd, and then you would determine these as based on those. So in other words, the 3rd and 5th vector can be anything they want, but we have to have some specific combination of these guys. So these are the ones we'd want to save that are actually linearly independent. So I'm going to write that out as a claim here, right? What my claim is that our original span of our original vectors were -1, 0, 0, 2, 2, 2, 2, 1, 2, 2, 4, 1, 0, 0, 1, and 2, 1, 1, 2 is actually equal to the span of these three here. So of minus 1, 0, 0, 2, 2, 2, 2, 2, 1, 0, 0, 1. Okay. Now, it actually turns out that this is a trick you can always do. Whatever the sort of pivot positions, those are the vectors that are linearly independent, and they are also the ones that you need to keep to not change the span. To justify this claim, though, right? I mean, in general, you guys wouldn't have to justify it because this is something that is always true. But just since this is our first example of seeing it, what I want you guys to see is that these two here can be written in terms of these three. So let's go ahead and see that. To see this, but I want to note that this guy, 1, 2, 2, 4, right? This third vector here, I'm claiming it's not necessary. Well, he's a linear combination of these two. It shouldn't be too hard to see that he is actually negative 1, 0, 0, 2, plus 2, 2, 2, 2. Right? If you add these guys together, you get this guy. So in other words, he doesn't contribute anything to the span because anything that can be built out of him can also be built out of these guys. Same thing with this guy, although it's a little bit harder to see, but 1, 0, 0, 1. Oh, sorry, this guy here. My apologies there. That's the one we're removing. 2, 1, 1, 2. So that guy right there, 2, 1, 1, 2. Well, that guy is actually 1/2 of 2, 2, 2, 2, right? Which would be 1, 1, 1, 1, 1 plus 1, 0, 0, 1. And that will actually give us 2, 1, 1, 2. So anything that can be built out of 2, 1, 1, 2 can actually just be built out of this guy and this guy. So deleting these doesn't actually change anything. So in other words, the span of this is the same as the span of this. On your guys' own, you can also go back through and you can actually check that the span of these three right here these three right here, we know that the span of these three is the same as the span here, but you on your own can check that these three are now linearly independent. These three are linearly independent now. Last little comment here, right, just as a little side note. If you guys want on your own, you guys can actually check that the span of these guys is actually a very special subspace. Span of minus 1, 0, 0, 2, 2, 2, 2, 2, 1, 0, 0, 1, actually is equal to the set of all matrices A, such that A equals A transpose, A an element of M2R. In other words, this right here is a nice little spanning set for the set of all symmetric matrices. I can let you guys check that on your own, but it shouldn't be too hard to believe. All of these matrices here are symmetric matrices, and if you notice, you can use these to build any symmetric matrix that you like, but I'll let you guys confirm that on your own there. Okay, so these two examples basically walked you guys back through looking at linear independence and dependence for sets of vectors. We also did a little bit more. We also learned, like in this example here, that when you check for linear independence and dependence, those three pivot positions, or those pivot positions, also correspond to the linearly independent vectors that have the same span. Those ones that would be parameterized are the ones that you can be safe in removing without influencing the span. Okay,